as well as band 41. Know that we used to have a huge product line for many bands for many other regions. So if you don't see or hear anything specific you're talking or that we're going to be talking about today, most likely we do have a solution, but these will be the more common products that are deployed, especially for private networks. So before we get started, let's do a quick overview of the common products we do have. So starting with the Nova series. So, and if you see the Nova product line, this is basically our all-in-one small cell that's going to have the baseband, the radio head, everything's all integrated in one box. And then so the 430, this is the 4 by 250 milliwatt. This one is actually an integrated antenna version and it's PoE powered. So pretty simple to deploy, set up, doesn't require much professional install to get this mounted and going. So this is a very good product for kind of lower coverage, but more outdoor focused deployments. So if you're looking for something to, very quick, efficient to deploy and have a coverage area that's not too great, you don't need to go several miles with it, then this is a good product for that. So GPS is built in as well, and there is 2 carriers. So in the LTE world, as well as 5G, you'll see the word carriers a lot. So there's single carrier is just one carrier that's being transmitted. In this case, you have dual, which is typically used for CA. So with LTE, you have a maximum of 20 megahertz you can use. So if you do 2 CA, so 2 carriers, we can do up to 40 megahertz, and we'll go into that a little bit more later as well. So typically for outdoor radios, you're going to use GPS, but if for some reason where maybe you don't have view of the sky when you're outdoor, or you could even deploy it indoor, but in that case, to keep it synchronized, you'd have to use 1588 as the other solution there. It is PoE++ standard, so it does come with PoE adapter, but if you had network switches that are capable of powering it, that would work as well. But so this is one common radio, especially for CBRS, and I think we have other bands for it, but for US market, this is a band 48 solution. We also have an external version. So if you were looking to deploy your own antenna, whether you want higher gain, in some cases you might deploy an Omni, so you want one radio to do 360 coverage, then you would go with the external route. So it's the same specifications as the integrated that is on the previous slide, just that this one you have the flexibility to put any antenna you wish. The other benefit of the external is for the dual carrier, it's actually each 2 ports is its own dedicated carrier. So you could, there's another mode called DC mode. So you could actually have 2 split carriers, say transmitting in opposite directions. So that's the added flexibility there as well. But overall, pretty much same, just the flexibility is with this radio. 436Q, this is going to be more of our flagship product that I think is still the most sold radio that we have. This is still LTE. All the Nova products are LTE. And this is 4 by 1 watt. So this pretty much takes advantage of the full ERP that's allowed for CBRS. So this radio is popular for doing large coverage outdoor. If you put a sector antenna on it, then you can hit that maximum ERP that's allowed within CBRS, making this the more popular product for outdoor installation. So just like the 430E, you have to bring your own antenna. You do have the flexibility to add 1 antenna or even 2 antenna, two parts. So, but Specification wise, other than being higher power, it's actually the same chipset components that are in the 430. So one nice thing is if you're configuring any of these Nova radios and you get different versions of them, the software is the same. So if you've configured one, you can configure them all. Um, and then also with these Nova radios, they do have an option called Halo B that's actually included with them, which is the embedded core. So we'll go over the core options as well and the flexibility there. But there's, one advantage with that as well with the Nova radios. This one is not PoE powered. So this one you'd have to run separate DC wire to power that. So that's the one kind of difference with the 430 compared to 436. But as far as the performance goes, they're going to perform the same, just with different coverage and power. So Nova 442i, this is one that's actually has a built-in Omni. So this product was released to kind of try to bring a simpler way to deploy a high power radio. As you saw with the 436, you have to bring your own antenna, so it just makes the installation a bit more complicated. But if you wanted a more simple, and the other benefit here is it's PoE. So if you wanted a PoE power but have an omnidirection while being, high power, this was, one radio that could make this much easier deployment. So if you have a need for, large 360 coverage, this is one that's kind of, with the built-in antenna makes it easy to deploy. Additionally, PoE++ was added to support, PoE power. So you could just run one cable to the radio, making, this a pretty easy to deploy high power solution. Performance-wise, otherwise, it's the same, just in a different form factor. Then we have the 846. So 846, actually, all the previous radios we looked at, they're all running the same Qualcomm chipset. This one's a bit different. It's running NXP. It has a higher processing performance. So this is more for like macro type performance. Uh, so it can handle more users. So it's got, more CPU power to run that. You know, so the big thing here is it's got 8 antenna ports, so you can do it supports 2 carriers, so each 4 ports is dedicated to one antenna. So it does 4x4. So in theory, you can get potentially up to double the peak data rates as you could with the previous radios we were looking at that did 2x2 MIMO versus 4x4. I would say in practice, it's very difficult to get 4 layers downlink to reach those peak data rates. But in very specific conditions and circumstances, there could be higher performance gains with this. But typically this radio is more, I think, deployed and used in situations where high mobility and high number of users is being used. That's where this radio will benefit a bit more versus the previous ones. Okay. Then we have the 452. This is the kind of flagship LTE solution that we have for band 41. So if you have access to band 41 spectrum, this is typically the radio that's being deployed for that. Similar to the 846, runs an XP platform. So it is going to handle more users. And one difference here is while it also does support 4x4 MIMO, it only has 4 ports. So what it does is those 4 ports are kind of shared between the 2 carriers. So if you did 2 CA, basically the power would be divided in half among the 2 carriers. One other difference with this one is there's only SFP. So you would, typically use optical interface or an SFP to Ethernet module if needed. But otherwise, it's fairly similar. performance with the 846. Okay, for indoor LTE, this is our main product for CBRS. It's Neutrino 430. So if you have indoor application, this is typically ready to go. And this one, like the Nova 430, it's identical specifications pretty much. It's just that it's in an indoor um, shell, so it's more for indoor deployments. And so it can support up to 2 carriers for CA and is PoE powered. So yeah, otherwise, if you've configured the Nova radios and Neutrino, it's all running the same software. So very similar performance specifications there, just indoor format. Okay, so now for 5G, the branding we use for that is Aurora. So it's similar to Nova in that the base station, it's all fully integrated, so you don't have a split baseband and radio head units. We do have that portfolio as well, but here we're more focused on the simple solutions that are more common, especially for private networks. So for the 5G Aurora line, the Aurora 243 is the main product we have for CBRS. So this was the first generation Qualcomm 5G chipset, which uses a single carrier, just a 2x2 MIMO. So very simple platform. But with 5G, you'll see that now we have access to up to 100 megahertz. Oops, sorry, go back. We have other bands for this as well. So you'll see a number of different bands listed here. But typically, if you're running, we'll look at that the other slide, but for bands that don't have the tighter ERP restrictions can use higher power. There is a higher power radio for those as well. But so some of the differences over the 4G, we have mostly it's going to be you have your higher megahertz, which can take advantage of 5G. You get higher modulation, especially on the uplink. So your uplink performance is going to be an improvement there. We can support more connected users. But yeah, generally with 5G, you're going to take advantage. If you have access to the wider channel bandwidths, that's where you're going to see a lot of the maybe throughput advantages that you will get over LTE. Then as far as the tech, the specs, we'll kind of go into that a little more in later slides. And then the Aurora 249. So the you'll see the number goes bigger. So the last 2 digits is the total power in dBm. So just FYI there. But you'll see that now we're going 2x40 watts. So for N4178, these bands commonly will be of higher power. So we're going to use a higher power radio. Other than that, the performance is identical to the 243, just higher power in different bands. Okay, and then for the indoor, we have the Stellar series. So Stellar is the name for 5G indoor, just like Neutrino was for the LTE. So at the moment, we have the Stellar 227. We have different bands for it, for 41 CBRS as well, with 48. But it's going to have, same chipset with actually the Aurora 243. So it's going to have similar performance to that. I think maybe less connected users. So it's got a little bit less CPU, but performance as far as peak throughput and specifications is going to be the same there. Okay. And then for CPEs, now when it comes to LTE 5G, it really depends what is the network use case. So you could bring your own UE, whether that's a mobile phone. There's many devices now. So depending on what your purpose is, you could go CPE if you're looking for more of a fixed wireless type application. But if you're looking for mobile application, there's many devices out there that support LTE and 5G. So here we're going to just show some of the common. We have a lot more CPs that are going to be shown here. Just some of the popular CPs that would be sold to match the radios, the base station side. So on LTE, this is our low-cost solution, or our lowest cost CPE. So this would be the Cat 16 or the Atom Audio 6LX. So the Cat 6 in LTE, the UEs are classified by their categories. So Cat 6 can support CA, but it's not going to support the 256 QAM on the downlink. So your downlink peak downlink won't be as high as maybe higher categories. But if you're just looking for the lowest cost kind of CP, this is the popular option for that. And then for Cat 15, this is our kind of the highest premium product for LTE that we have. So it's got a much bigger antenna that's integrated. So you can see that it's 18 dBi for CBRS. And then it's category 15. So you're going to get some additional features such as the 256 QAM on the downlink. But otherwise, actually, the software is the same between the LTCPs for the Cat 6 15, maybe different firmware file, but the software is similar. So if you deploy both of them, it will be very familiar to configure once you've configured them before. We do have different bands. Not all of them are listed here. So if you don't see like a certain frequency band that you might be interested in, we do have support for many other bands with other models as well. And then on the 5G front, we brand them as Photon. So Photon, this is our basically our outdoor. At the moment, we just have the one outdoor CP. We are actually under trials for a higher gain version of it as well. But the 5G CPs, they support a lot of different bands, not just the few that we were doing previously with LTE per model. But with 5G, you can also do backwards compatibility to LTE. So that's nice if if you have a mix in your network, or you're just wanting to maybe future-proof and deploy 5G CPs on your LTE for eventual 5G replacements. So you do have that benefit if you go with the 5G CP. So you don't have to use connected to 5G, but it can do both. Then you'll see that there's actually a couple different models you can get. So if you get the one that's more like we have models like NR11, NR6. So the NR11, if you look at the bands, you'll see that they are more restrictive because the antenna is more tuned to those frequencies. NR6 version, you'll get access to a lot more bands, but the antenna is not going to be optimized for any particular one, so the antenna gain will be a bit lower. So if you do see different versions of the CPE, there will be a little bit of impact on the antenna gain, depending on which model you select. Then for indoor, we have a 5G indoor as well. So similar specs to the outdoor, just in the indoor format. And then additionally, it will have the Wi-Fi 6 built in as well. So if if coverage is, if you have good coverage for nearby homes or wherever you're trying to connect, the indoor is a pretty good option for that. Okay. So that's quick product overview. Definitely did not cover a lot of the solutions. We also didn't cover the core since Blue Arcus is going to be covering it from their end. But so end to end, when you're looking to deploy cellular, you do need the the RAN, which is going to be the radios we covered, the UEs. You're also going to need the core network. Baicells, we have core solutions, whether that's integrated, external, but there's, a large number of other vendors that have core networks as well, that, maybe specialize and have, more features for that as well too. So we'll save that for a later section with Arcus to cover their side. But for now, let's go into kind of overviewing the basics when it comes to, and we'll start with LTE. And why we start here too is there's a lot of crossover between LTE and 5G. So you'll find that once you have the basics and fundamentals of the LTE, on the 5G side, there's a lot that follows that, and there might be some renaming of different parameters or fields or names of things, but the principles are the same in a lot of areas. So we'll start with LTE first, get those basics down. So in LTE you have, and it's the same with 5G, you have TDD and FDD spectrum. So TDD is going to be more of your mid-band to high-band frequencies. So that's time division. So basically downlink, uplink are transmitting on the same frequencies, where the lower bands, they might be split. They might have a different frequency for uplink and one for downlink. So in what we're going to cover is mostly just TDD, since that's the more popular deployments, since mid-band and upper bands are typically what's deployed, especially for private networks. For FDD bands, those are typically on lower bands that are going to be owned by operators. So unless you're an operator, you're typically not looking at FDD. Now the specs a lot, especially later on. So when LTE was initially launched, the initial specs supported 64 QAM downlink, maybe even 16 QAM uplink, and then over time that changed to support up to 256 in both directions. I do have some examples of some data rates comparing with our products, and which kind of tied to what the specification supports. So if you looked at, let's say, this 220 here in TDD. So if we look at the TDD section, so 220 download or megabits on the downlink. So that's assuming we got 64 QAM and 4x4 MIMO. Now, again, I should say the 4x4 MIMO, I wouldn't, that's more like on paper, and in lab you can reproduce these things, but in field, again, 4x4 is difficult to obtain. So if you're designing your network, trying to, figure out how much bandwidth or how many cells you're going to need to serve a certain bandwidth for a certain area, then I would focus more on the 2x2 MIMO, even if you have 4x4 MIMO, because it's not guaranteed. So this would just give you an example. So in a single 20 megahertz channel, you could directly get up to 220 in TDD2. So we'll review in the later slides what does this mean with the subframes, but you do have different configurations for your downlink to uplink ratio. For 256 QAM, and then same kind of goes 256 QAM. So 256 QAM, you do need you need to be very near the cell you have to have very good path loss and very good signal to get the 256 QAM. But these are just showing, again, peak data rates. So if you're near the cell and you had scheduled all the resources, you can get up to 145 megs on 20 megahertz TDD2. And then if we looked at the difference between 256 and 64 QAM, you see that will drop a bit, right, to the lower modulation. Now, this is TDD2, which is more towards downlink. So we'll look at that later, but TDD2 is going to be more downlink and maybe just a little bit of uplink. And for an example with the uplink, we have 35 megs. But you'll see that this is for one single 20 megahertz channel, but now you see TDD 6. So there is a subframe assignment that you can configure so that you get mostly uplink. So you do need to, change the downlink to uplink ratio based on your application. And then these are measured in 20 megahertz. So if you did CA, you would effectively double these numbers if you were to configure CA with 20 plus 20 megahertz. And then again, 20 is the the highest channel size that is supported within LTE. And so that's part of what attracts 5G is you'll get the higher bandwidth capacities, and you don't need the complexity of aggregating multiple channels to hit those higher bandwidths. So if we look at the network architecture of LTE, we'll see on the left side you'll have your RAN, the radio side. You have your eNode B, which is the base station, and your UEs that are connected to that. And then you have your different interfaces that connect. You have your interface between the eNode Bs for handovers, and then you have your interfaces to the core network, and then all the different elements. So the MME is going to be what the initial connection from the eNode B to the core network is. MME is doing all the control plane signaling, the mobility anchoring, and then that's going to talk to HSS to authenticate. And for your user traffic, you'll see that the user traffic, so S1U, is going to be split to a separate gateway, the serving gateway, which then forwards to the packet gateway, which then forwards out to the rest of the network. So all these elements, these are just the core basic elements that make up an EPC. There can be more. But we'll see with 5G what changes in the later slides and the differences there. So kind of just doing a brief overview of what those, what the responsibility of those different network functions are with an LTE core network. And then we'll see later with 5G where some of these get merged or split into their own different functions. But yeah, for the main ones again will be your MME. So if you're configuring a local core network, you just need to know what is the MME IP, what's the IP of my core that I need to connect to. Once your base station connects to the core, it kind of does everything from there as far as the control planes. It will inform the base station, which gateway to send the user traffic to and so forth. And it's going to authenticate your users through the HSS. So your serving gateway is more facing the base station side, and then the packet gateway is going to be more facing towards the exit of the network, and that's going to be, how it accesses the internet and other pieces of the network. Okay, so we'll review again some of these. But so the channel bandwidth, again, we have up to 20 megahertz with LTE. So with Baicells, most of our LTE eNode Bs can support CA doing at least 2 carriers. So the maximum basically you can get is 40 megahertz with a Baicells LTE eNode B. And then if you're seeing lots of different band numbers, you can see that based on the number, it's going to be part of a group of FDD bands or TDD bands. But in our case, we're mostly focused on CBRS, which is band 48. So that falls into the TDD, as well as 41's common deployment as well, especially with the tribes getting access to that spectrum. And so we're seeing a lot of activity there as well. So that's also a very common band. But and then 5G we'll see later has many more bands as well. So and then again there's different types. So you might see reference to FDD as type 1 or TD as type 2 if you're reading the specifications of 3GPP. But again, these are the two types of frames that are supported within LTE. And then if we look at the frame itself, the frame's going to be split into 10 milliseconds, so the frame is 10 milliseconds long. It's going to be split into 10 1 millisecond frames, subframes, as it's called. And then the makeup of these subframes is the TDD configuration. So the TDD configuration is going to basically determine which subframes dedicated for downlinks. You'll see that illustrated as a D, and then uplink illustrated as a U. And then anytime you're switching between downlink to uplink, you'll see an S, which is the special subframe. So within the special subframe, it's going to determine how much is for a downlink, and then what is the guard period, and then how much of it is uplink. So most of this special subframe will actually be towards the downlink with a little bit of guard period and a little bit of uplink. So we'll see that even so if we look at this diagram here, we'll see there's one, if we chop it in half, this frame to half to 5 milliseconds, you'll see how this makeup, because every 5 milliseconds it's just repeating. Most of the common subframes do this. There's some exceptions, especially with subframe 6. You'll see that it's got two different patterns here. But in this case, we have a downlink, special subframe, uplink, downlink, downlink. So that's we would call this subframe 2 or TDD2. So here we have 3 downlinks to 1 uplink. And then I did note here at the bottom that depending on the base station you have, our like first generation solutions that were Intel based, we could support subframe 0. Qualcomm didn't support it, but they do support subframe 6. So you'll see that any modern Nova series is going to support subframe 6. You would only use subframe 6 if you actually have a need for if your application is mostly upstream, like say video cameras. This would be the situation you might consider using subframe 6 because all you care about is the uplink. But in the typical application, it's usually more downlink focused. So subframe 2 is typically the most popular, followed by subframe 1. And we'll look at kind of the chart here illustrates that. So we'll see, we were talking about subframe TDD2 last time. So you see, over the 10 milliseconds. So in the one frame, what does that look like? So yeah, so you see downlink, it switches, then uplink, then downlink, downlink, and then it repeats. So you'll see that the lower configs here, so config 1 and then config 0 is going to have more uplink. And then we did later add that config 6 for the newer Nova radios to support more uplink. So basically this chart basically determines, and by 3GPP defined, they've kind of preset, these are the TD configs that are supported. Later on with 5G, we'll see that we have a lot more flexibility. But there is this simple defined chart of this is your downlink to uplink ratio options, essentially. And then within that special subframe, you have your special subframe pattern. And I highlighted here, you have special subframe format 5 and format 7. Format 7's set by default and is the most commonly used. You'll see that the difference is with subframe 7, you have 10 downlinks. So we'll look here. So most of the airtime is towards downlink. And then there's a little bit of nothing. This is the guard period, followed by some uplink. This is the most common. And typically you would only need to change this if you're trying to do for much longer coverage. If you're trying to go, say, more than, say, 5, 6, I forget what I think we have it on later slides. When you go when you go many miles, at some point, this guard period is not going to be enough. So if you need to support much larger distances, then you're going to have to increase your guard period. And so one way to do that here is we're just going to modify this special subframe pattern. So if you're at 7, but you want to go, say, 8 miles, then you should probably switch to format 5 to increase that guard period. So you see in subframe 5, special subframe 5, it's a huge guard period in comparison to 7. Here is a example. This is actually came from a Cat 4 CPE that's supported up to 64 QAM downlink and 16 uplink. But this is just an example MCS table that maps it to what is the peak expected throughput based on the cell's configuration. So we can see how just from changing the subframe assignment from a 3 to 1, which remember would be like a TDD2 config, to a TDD1 config, that configuration obviously is going to dictate what your peak throughputs are for your uplink to downlink. So you can see you can effectively double the uplink by changing what's typically defaulted as a TDD2, a 3 downlink to 1 uplink ratio. So if you add another subframe towards uplink, you can see you're doubling that uplink. But one difference is with LTE, the uplink is typically just one data stream. So it's whereas downlink is 2. So you're not gonna see the same higher throughputs with downlink that you are with uplink. A lot of that's just to do with the single stream. Uplink is mostly what's supported here. Okay, so here we can see kind of a summary of what we just discussed. So some peak data rates examples at 64 QAM, what you could expect with subframe assignment 1 versus subframe assignment 2. And then also, yeah, this is a good one too. So when we're talking about the guard period, and so when you're on the special subframe pattern 7, which defaults, it looks like actually the theoretical with just the 2 guard period slots there, you could go up to 11 miles in theory. So if you ever need to go past that, which if you're running high power base stations, then that would be the situation where you would have to change it. So you can see the theoretical limit now changes to 46 miles with the special subframe 5. Okay. So with the 2 carrier ENLBs, you have basically 2 modes that we typically advertise. So you have your on the left side, you'll have what we call like the DC mode, dual carrier mode, and then right we'll have CA mode. So the difference here is with DC mode, each of these 2 cells that are being broadcasted, they're both independent from each other. So they're within the same physical radio hardware. And they're just broadcasting 2 different channels. They're not aggregating them. So why you would do this, typically you would do it you have 2 different physical antennas. So those physical antennas are covering different areas. So for an eco reason, you could, in theory, just deploy 1 or 2 radios to do 2 or 4 antennas to cover an area. You wouldn't have to buy a radio per antenna at that point. So there could be some cost savings there. For CA mode, this is more a performance oriented. So this is going to be, typically just 1 antenna is going to cover with the CA, and you're going to be doubling, the capacity that you would get from a single carrier. So instead of, just having UE have access to up to 20 megahertz, you're going to have that UE could have access up to 40 megahertz. So you're going to be doubling the potential throughput for that, connected device. It doesn't change the total aggregate throughput of the base station. So the so in both scenarios, the base station has up to 40 megahertz of bandwidth, but it's just, are you trying to aggregate them in a single direction or coverage area, or you're trying to split it off into separate antennas? That's typically the logic here. So on CA, some things you'll see reference of. You have basically the two types of cells. You have your P cell, or your primary cell, and then you have your secondary cell. So when you configure CA, the second cell is basically, as it's stated, it's a secondary. So all your devices would still connect to the P cell. And then once throughput is being scheduled, or your resource blocks are getting scheduled, that is when the UNOB will start assigning both cells. So, and also it's when the user attaches too. So when the UE attaches, it's going to check its capability, and it's going to determine, does it even support CA in the base station configuration? If it doesn't support CA, it won't, that particular UE won't be scheduled anything in the S cells, but it would only get scheduled in the P cell. But if it does support CA, that would be configured during user attachment, and then the base station would schedule accordingly. And our base stations just evenly distribute the PRBs between the PSL and SL. But yeah, just know if you had configured CA, connected a device, and it's not getting, you're noticing it's not getting the double throughput, or you're not seeing anything scheduled in the SL, then typically it's just that device, that UE that attached, did not support the CA. But there's different types of CA as well. There's contiguous CA and there's non-contiguous. So we've seen that sometimes a UE might claim that it supports, say, band 48 CA, but it might only support, like, say, a contiguous CA. And so if you configure non-contiguous CA, then it still won't work. So know that there is some difference here. Mainly contiguous is that, in the simplest terms, that both P cell and SL are adjacent to each other. But non-contiguous CA would be, there's going to be a larger gap between the two channels. CBRS, this will be common. Non-contiguous will be common, as you don't know when, which of the frequencies are available. So it's common that you might get in CA configuration, you'll have one, maybe P cell and SL are in very different locations on the spectrum, just based on the availability of the channel and what the SAS authorize. And that's part of the intraband, as we're talking. Interband would be you're doing CA across different types of bands. So say band 48 plus band 41. So you can do that as well, but these are the definitions of the different types of CA. And this is all the same in 5G as well. So 5G can also support CA in the standard, and so all the terms that you see here actually apply to 5G as well. So on LTE, we're talking about the network identifiers. These are the things you'll learn when deploying a network. So first you'll have your PLMN. So traditionally, when carriers are deploying this, they are assigned their own unique PLMN. That's, so T-Mobile, AT&T, Verizon, they're going to have their own PLMNs, actually a number of PLMNs. And that would be what you as an operator, you would configure the PLMN on your base station. So that base station is going to be broadcasting this PLMN. And in that broadcast, that's telling all the devices that are doing cell searches, which network are you, and, whether or not you should connect to that cell or not. in private networks, CBRS actually has its own defined PLMN. Here at Baicells, we launched prior to CBRS, so we actually registered our own PLMN. And so if you're buying a full Bicell solution, you'll see that the radio comes configured with our PLMN, but you can change this up. But typically for private networks with CBRS, there is a dedicated PLMN just for CBRS private networks, and you can actually there's like another 4 digits, the IBM number after this PLMN that you can uniquely assign to yourself by registering for this. So there is a way to do this as well. And then also there's like testing PLMN and a private PLMN. So if you see PLMN 999 and then whatever the 3 digits afterwards, that you can assign and you can use that as well. That's like blocked out just for private uses. So if you don't have your own PLMN, that's very normal. There are shared PLMNs you can use. There's private PLMNs you can use. If you buy from Baicells, our PLMN's already in there. So normally this isn't anything you need to consider about. And if you're buying, or if you go through a core, like say through Blue Arcus, they've already handled this as well with the PLMN and the SIMs. So um, so the next so if you look at this diagram, you'll see the the PLMN's like the main thing that's being broadcasted. Also that's being broadcast, you have your TAC, your tracking area code. This as it states, it's like an area code. So if you have a big diverse area of many cells, it might make sense to divide them into different TACs. For private networks, there's typically not too much reason to do this. You could maybe help with some of the idle messages, but yeah, there's the typically TAC one is going to be used. So this number you'll just leave it at 1 typically. Then you have your ECI, which is your cell ID. This is the ID that identifies the cell itself. So this ID should be unique across the network. What we do is this ECI number, if it's a Baicells radio, you buy this ECI will be randomly like kind of generated based off the serial number. So this should be unique. So if you only bought Baicells radios and you didn't want to define and plan out your own cell IDs, one good thing is you wouldn't have to worry too much about this, as it's already they're already set uniquely, so you wouldn't have any conflict there. If you did mistakenly have two base stations on the same cell ID connecting to the core, basically they'll start flapping their connection with the core. The core will keep dropping them. So that would be one issue you'd see. Then you have, and this is part of the confusion, because base stations, they basically have two IDs. They have the ECI cell ID. So that's what uniquely identifies them on your network. But then you have your physical cell ID, the PCI. This is more like for identifying, you could think of it more like identifying the antenna. But this doesn't have to be unique. It should be unique in a way, and we'll cover that a little later with PCI planning. But this is how, like, you can think of it too as how does the UE identify the radio, the base station. The UE will identify more based on the PCI, where the core network will identify the radio based on its ECI. Okay, then for the equipment identification, that's the main number here is the IMSI. So the IMSI is the unique SIM card number. But then the equipment, similar to how a MAC address is on network devices, the IMEI is like that unique identifier for the device itself. So, but how the network identifies each user is going to be by its IMSI in LTE networks. Okay, so covering this a little bit further. So with the ECI, so this is again the unique cell ID that for the network. So every cell will have their own unique ID. The ECI is actually made up of another BID and cell ID. Uh, for this today's purpose, we don't need to go too much into that. But at the very least, you just need to make sure that the CCI number is unique on the network. And again, if it's a Baicells radio and you just plugged it in to your network, it's already unique. So this part you won't have to worry too much about. But we'll later on when we look at the configuration of the radio, we'll look at this and where you can configure it if needed. All right, now the PCI. So this one, the range is more limited. So you can see the range is from 0 to 503. It's made up of two components, your PSS and SSS. So the most important component here is the PSS. This is a mod 3 value, so it's going to be 0, 1, or 2. And this defines, depending on what your PSS is, this is going to define where your reference signals, your elements are within the base station. And this is how the UE is measuring the signals levels of the base station. So now if every base station had a different frequency, this doesn't really matter too much. You could technically have the same PCI in every single radio and it wouldn't hurt too much. Where this is important is when you're doing frequency reuse. So if you're trying to reuse the same frequencies in the same geographical area where there could be overlap, this is where PCI is the most important because if the PCI value is the same, or this PSS, mod 3, the value of the PCI, you'll get your PSS. If that becomes the same as another neighbor cell, which is on the same frequency, this is where you'll have this kind of PCI conflict. And this now the UE is getting interference from both cells and it can't measure the differences between them. So now the performance of your network will be bad. And then even the UE trying to access the network, you'll have a lot more fail rates there, just due to the noise and issues there. So the PCI is really so there is some like best practice stuff that could be dove into in another session. But when you're planning, the kind of the key here is when you're planning your network, typically you would think about frequency planning, but in LTE, and this actually applies the same exact thing to 5G. PCI planning is like another critical kind of importance. So what we do for our base station, at least out of the box, is we randomize the PCIs. So we have a kind of it will generate something. I think it's also based on serial number, but it will at least try to make sure that random is still better than nothing. So it'll still try to random assign PCIs to try to avoid this PCI conflict. But it's still better that if you're planning to use the same frequencies, you're doing a lot of frequency planning, PCI planning becomes another kind of key practice that you'll need to strategize on when designing your network. So yeah, this kind of just another slide just talks about here when we talk about the RS reference signals. So as mentioned, the PSS part of the PCI is defining where the location of the reference signals are. So there's three potential locations. If these ENOBs are the same frequency and the PSS is the same value, the UE cannot distinguish between the two. But if the PSS is a different value, it can. So it would avoid some of the issues described here. like maybe even handover flapping a lot because it's not able to determine the proper signal levels. So, and yeah, so and also like so when you're looking at the UE metrics connected, so if you're whether it's a phone CP, if you're looking at it, you'll typically see the RSRP is going to be like that signal level that you're measuring. That RSRP that what is measuring is this reference signal. So again, if that reference signal is in the same location, same exact channel frequency as another neighbor radio, that's where you'll run into all these problems. Um, so yeah, just all you have to do is make sure that at the very least, if you have any cells reusing the same frequency, just try your best to make sure the PCI PSS is a different value. And there's I think it's simpler just to pull up like Windows calculator, do a mod 3 of PSS. You can make spreadsheets as well to try to strategize. And typically how people do this is they like 0, 1, and 2 is because typically in a operator traditional deployment, they might have 3 sectors on a tower, and those 3 sectors are, reusing the same frequency. So that's kind of where this specification comes from. But you could have like the PSS be based on the direction that the antenna is pointed. And so you could, if you had a spreadsheet, you could, divide it that way. Like if it's, north, maybe that's 0. If it's southwest, it's 1 and 2. So you can kind of, try your best to make sure that all the PSS antennas are in one direction. And that would try to avoid some of the um, but that's more like a macro type, like traditional way of thinking about this. The things get a bit more complicated with small cells and a lot more deployments, but yeah, this is a section that could spend a very long time on, so we're not going to do that for today. But just know, yeah, PCI is something that is quite important in networks. We do uniquely assign it, but it's better to try to make sure that you are at least paying attention to what the PSS value of your PCIs are, and avoiding neighbors with the same PSS on the same channel nearby. Yeah, on the tracking area code, and again, this is actually the same with 5G too, but we'll set this to 1 by default with Baicells. It's just for tracking. That's how the core network tracks where is the user. And so if the user went idle, very common in mobile phones, that they'll try to locate that user by sending a tracking area update. So that TAU goes to all the base stations that belong to the same TAC. So for small networks, private networks, it really doesn't matter too much. But if you had thousands of cells, you probably don't want to send a TAU to thousands of cells trying to find this user. So that's why TACs exist to try to divide by region. So okay. So that covers that's like a very brief walkthrough of 4G. I think maybe what we'll do is go through a quick configuration or just a quick overview of the base station side. So maybe we'll stop here, and we'll switch to that. In the meantime, if anyone has questions, feel free to send it in the Q&A while I get while I load the web GUI for a base station here. So by default, just so you know, so what I'm doing is I'm logging into, this is going to be I believe a Nova 430 radio. So this, we're going to log in, by default it's admin, but newer software, this is going to use enobB at, and then it's going to be like ABCD followed by the last four digits of the serial number. So if you ever had any help with that, just know that the default password did change. So I'm going to do that here. Okay, I might need to relog in to here, find it. So we'll go into the cloud core here in a minute. Just need to verify the last four here, 0127. Okay. Okay, so when you log into the base station, this is going to be, it depends on which version you're running. Here we're on version 5.0. 3.1 will look very similar to this. So you'll have this dashboard here, and this is going to give you the quick indication of how things are connected. And mainly what we're looking for is, it will state is the cell active. So if it's active, it should be transmitting. There's like a little radio here you can highlight. It shows that it's transmitting, it's on. Right now there's no users on it. So this one's kind of a little bit already configured, but we'll walk through what you would typically do here for a basic settings. And then on this page, you can click these little modules with little arrows to make changes here. You can also go to the individual pages as well. But here, based on what we've walked through with some of the LTE overview stuff. So firstly, let's go to this enobB information, and we'll see a lot of what we kind of walked through already. So here we have our subframe assignment, and remember we were looking at that chart before. So you have TDD 1, 2, and 6, and you can see where the downlink uplink ratio is changing. Then you have your special subframe pattern, and then here we actually have a few different options, but as mentioned, for the most part, you typically won't ever change this. It's only really necessary if you need to change that guard period for very large coverage. For CBRS, small cells, this is typically always going to remain at 7. The carrier mode, right now it's grayed out. So one thing with the Nova radios is if you don't have a license, you won't be able to change this. So in this case, I didn't have the CA or DC license. So I won't be able to change this for demonstration, but this is where you would change if you want to enable CA or DC. But here's your TDD configuration. So you can change that here. And then for your frequencies, you would change that on the cell information that I just clicked. So here now, and I'll show you later, but right now I'm in band 48. I can actually change it to other bands here. And normally in band 48 CBRS, you won't be able to change some of these settings because these settings should be set by SAS. For the time being, I just have SAS disabled for demonstration purpose. But typically a lot of these will be grayed out. But if you weren't using SAS or just testing, here is where you could set your channel bandwidths. So as we discussed in LTE, you can do up to 20 megahertz channel size. You have your frequency. So you'll see that the frequency is defined with the parameter ERFCN. So it's just a one-to-one map. There's calculators online. So we try to at least show what the ERFCN equals to which frequency here in the GUI. But if you didn't have that information, there's many calculators and charts online that you could look up the RCN to frequency. And then PCI. So these were, not set by me. This was already set 350. If I was, again, trying to coordinate, I'd try to find if there's any cells nearby and make sure our PCIs aren't conflicting. And then the cell ID, this is uniquely generated already. But you could, if you wanted to define your own cell IDs, you could do that too and change that here. I do have the ability to turn on off the RF. So for lab, I like doing this. Like if I don't need to use it, I'll turn this off. For field, for commercial deployments, typically you won't change this, but maybe if you're trying to troubleshoot something, maybe you suspect there might be interference with another adjacent cell, you could, turn this off temporarily. You can change the different power levels. This is a 430 that doesn't support, it only supports 2x2 MIMO, so your only options here are two. If we have a 4x4 MIMO cell, you'll have up to four here as well. And then you can change your power levels. And then PLMN. So PLMN, this one already has the Baicells PLMN pre-added. But if you had your own PLMN, wanted to find what that PLMN is, if you go with another core network, they'll typically, work with you on what that PLMN should be. So if I needed a different PLMN, I could certainly add that here, and then I can, add, delete them as needed. And then if we go to the core network section, this is going to be more towards the core parameters. And this PLMN is going to be bound to a specific MME. In this case, okay. So you could have multiple PLMNs. So this is something called like MOCN. But if you wanted to broadcast multiple PLMNs, you're sharing your radio with another network operator, you can certainly do that. You could broadcast multiple PLMNs and then map that PLMN to a different MME. In my case here, the MME is 127001, which is itself. The reason for this at the moment is because we have this Halo B is on. Halo B is the name for our embedded core. So if you went with, this is going to be by default enabled for this. But if you had another core, you would go to normal mode. So from normal mode, you can now modify and bind your different PLMNs to different MME IPs. That's how that would work here. The other thing to note is when you do a local core or a third-party core, you'll want to switch this S1U on. Otherwise, you won't have user traffic. That's an important thing to note. And there's one thing a little bit unique with our radios. So when you have Halo B enabled, it will toggle this LGW, local gateway. So local gateway is going to, basically this is our LIPA, our local breakout. So it won't send the user plane to the core. It takes the user traffic and steers it locally to the base station's gateway. So this is something that we do a little bit unique. That way, because we're using the embedded core with Halo B, we're not running like the full blown, like all the different core elements. And we also interface with our cloud core, which I'll do a walkthrough with as well. But we don't want to send any traffic to Microsoft Azure where this is being hosted in. And so anyways, the LGW is always set to on when you're using Cloud APC or Halo B. But if you're using third-party core, you want to turn this off. So just pointing this out. So you would turn LGW off, and then you would go back to core network, and you just make sure that when you're in normal mode, you would set this switch to on. to basically enable the user plane. And then at that point, it's going to send it in the traditional way. So your control plane, your S1C, your S1U are all sent to the core you define. And you're defining the core by its MME IP. Okay. Let's go back to status here. So yeah, that's like really a lot of the basic configuration we just walked through. So those parameters, if you recall, we already discussed through them what their purpose kind of is. And so if that's all you did, like that would be kind of enough. Now, CBRS throws another wrinkle into things. With CBRS, you do need to use SAS legally to, connect and get authorization from SAS before you're allowed to transmit. So that should actually, I think, be enabled by default, but in this case, it's disabled on purpose. But what you would do here is, if it's a CBRS radio, we call this primary country code, but I put it other, meaning not within the US. But so if you're in the US, you have a couple options with SAS. The main one is domain proxy. So when you use domain proxy, it's going to send basically this OMC on the cloud is acting as the proxy. So and this base station's already connected to this to the OMC. So through that OMC connection, which is TR69, it's going to get information from the OMC from the SAS. So the OMC is the middleman in this case, talking to the SAS. And so this is really the main one, because with domain proxy, you don't need any additional certs. There's an option to talk directly to the SAS, but if you go this route, you'll need to purchase some CBSD certificate, because the way the wind farm wrote the rules, if your device is going to talk directly to SAS, you need a certificate. So there's a little bit of, it's not the big cost, but there's added cost with doing that. Where if domain proxy, if you're already using Cloud Core, there's no extra cost to it. So most people will just use the DP. And then you'll notice that, well, you also get a couple options here of how you want to register a SAS. So if you wanted to define all the install parameters right here on the radio, you can do that. And then also, this is totally optional. You could do it all here, like I'm showing you. You could also, from the to advanced. So if you go to advanced within Cloud Core, I can do the same thing that we're doing on the radio, but right through the OMC. So you don't have to log in directly to the radio to do this. If you're using the OMC, you can go ahead and configure that here, and you'll see you have the same, similar options as you do configuring it locally. But going back to this, we can go ahead and basically you would input, if you haven't deployed SAS before, or sorry, CBSDs before, this might be new. I think many have joined here have or are already CPIs, but there is a process. So if you've never deployed CBRS and you don't have a CPI, there are separate classes you can take to get CPI certification, and through that certification, they walk you through, what are the requirements, what are the install parameters, what do they mean? So you would just fill them out appropriately. If you have a CPI, you'll have your own unique ID, name, and you'll have a certificate that you would go ahead and you would upload here and then save it. Once you do that, then you're good, basically. Then it's going to talk to the OMC, which is going to talk to the SAS. I think it might be actually a little easier doing it from the OMC because the interface is maybe a little nicer. But you could, input the same things and then basically hit OK and save your SAS parameters here as well. So yeah, so you have two places to enter it. There's the other option here called the multi-step. So if I go to multi-step, you'll see all the installation parameters are gone. All that's left here, you have your user ID, maybe in the antenna gain. So even though antenna gain is an install parameter, the only reason we need this is we need to tell basically the OMC what is the gain, because the OMC will take the max ERP is set by the SAS to determine what the antenna gain is. And if we do multi-step, where the OMC has no idea what is the antenna gain. In this case, it should be 11. Then this should already be pre-filled out, technically. If this was reset, I think this might have been manually changed over time. But yeah, so you mostly use the user ID. The user ID is going to be when you sign up when you have a SaaS account, that you have a unique ID that belongs to you. And if you use Cloud Core, if you're registering a Cloud Core account or you have a Cloud Core account, you can go to your subscriptions page, billing page, and you can actually select, there's an option to do SaaS billing. And if you do that, that's like a quick way to like programmatically generate a user ID. So it's going to call an API to Google SaaS to generate a user ID for you. So if you are new to CBRS, deploying CBRS, that's kind of a quick way to do it, is just generate it through Cloud Core to get your user ID. But now going back to the difference here. So again, single step, we just put it all and then all here, save it. And once that's done, basically you're finished with registering. It will walk through the steps to get registered and then provide a grant. Where with multi-step, you didn't send the install parameters. So if you did it this way, the only way to get registered with SaaS is you have to log into the SaaS portal. And so from the SaaS portal, you would then finish the registration. So why you might do it this way is if it's just a preference thing. So you might have like a CPI on staff that is more like a sysadmin and just wants to do it all from one dashboard. So in that case, multi-step could work because the person physically installing the radio doesn't have to be a CPI. They can just do multi-step and then let the CPI that might be more central, let them finish like inputting the installation parameters and signing off on that with the SaaS to get them authorized. So then the other things to point out that are maybe a little different with us compared to other vendors is we added some other parameters here. We have legacy mode, which now is not very relevant, but when CBRS first launched, there was a lot of old like band 42, 43 CPEs that didn't support band 48. So when we did legacy mode, instead of broadcasting band 48, it's going to broadcast 42 or 43. So, and today, like this is almost never used. You have you can set your priority because the thing is when we register with the SaaS and we get the spectrum inquiry response, and we have to make some decision based on what the SaaS provided. The SaaS only provides a list of channels. The SaaS doesn't assign these channels for you. You still have to make the decision of the channels available, which channels should I pick? So that's what these preferred kind of SaaS settings are. So you're going to set, how we do it is we give you like what's more important to you. Is power more important, for example? Because in that spectrum inquiry response, we can see what's the max ERP for each of those channels that are available with SaaS. And then you could, so you could, maybe power, maybe you don't want your coverage ever to change. So you could use that. You could set what is your preferred bandwidth. Typically it might be 20, but if you have a lot of cells and you're trying to be more efficient with spectrum, you might lower that. You can even define what your preferred power is. And you might, even though it's CBRS, you can still channel plan. So you might decide that this cell I want to be at 3600. And if 3600 is not available for some reason, well, I know the upper 50 megahertz should be available, so maybe my backup channel is this one. So these are the things you have a little bit of flexibility to modify and change. So then you could save this and then now you have your preferred setting. So it's still important that even with CBRS, you still kind of think about the frequencies you're going to use, because if you left this blank, like you just left it at auto, and I think Cloud Core labels it better, like Cloud Core would just say auto, it's just going to pick from the top of the list. Now, if it's Google SAS, Google will try to actually arrange based on what it thinks is the better channel, but it's not perfect. And if you use federated, I don't believe they do this, so you always get the same channel. So while you could leave it at auto, it works, but if you're deploying a lot of cells, it might, you'll probably still be better off doing your own, like thinking about like what frequency channels you want to assign. Okay. I know we're getting a little long, so I think what I'm going to do is maybe I'll speed this up quick and then jump to the 5G slides. So, um, but now that I'm already in Cloud Core, just to show you the quick features here. So in the OMC, you have your monitor. You can switch, you'll see there goes a toggle here. I can switch between CP view, B view, Geno B view. So this is a test account. I don't have many devices in it, but this is how you can get a quick view to see if they're online. You can make changes to the radios similar to how we're changing them directly. So you wouldn't necessarily need to go directly into the radio, configure it. You can do all that right from this monitor page. And you'll find like typical functions that you would normally see with kind of network platforms you can upgrade. And there's performance KPIs. We don't have time to go into that today, but the OMC is basically how you monitor and manage your equipment. And there's different toggles here. The Cloud Core page, this is more like your billing page, is how you can change your subscriptions and add more users if you want different users to your accounts. So boss would be if you're using our Halo B or Cloud EPC. Bosses would be for you managing your SIM cards and activating those SIM cards. If you go with but if you're using say Blue Arcus, the core network, then you wouldn't need to use boss. You would only use the OMC. And this is kind of optional, but most likely you'll still use your OMC because you might still want to manage your equipment this way, but also it still acts as the connectivity to SAS. So you might still be using the OMC even with a third-party EPC. You could always get the OMC local as well. You don't have to use the cloud version of it. And the other thing you could consider is, well, if you just don't want to use the OMC anymore, you just want to keep with, say a third party, you don't want to use any other softwares, then for SAS, you would definitely use direct SAS then. Then you don't have to rely on the OMC to connect to SAS. But no, you do have to like upload. There's going to be a direct SAS cert or CBSD cert that you'll have to get from us to upload into it because they're unique per serial number. Okay, so let me switch to the slides here. And we'll cover 5G. There is a lot of like initial overlap with a lot of what we talked about the LTE, but there's also a lot of changes with the architecture and design of 5G. So when 5G was being, the specifications of it were being drafted, really, there was a lot of new use cases at this time that were being discussed. And compared with LTE, LTE was mostly like a mobility broadband play. There were like narrowband IoT. There was like some other things there, but like it wasn't like one radio could do everything, and there was a lot of limitations with the way LTE was designed compared to where the future was heading. So you'll see this kind of triangle is very popular and when reviewing what is 5G. But it basically goes to with 5G, they wanted to solve like they wanted to serve more purposes, more applications. And 5G was no longer just catered specifically to operators. Well, that's, a lot of these use cases still go there, but 5G is there's a lot more, surrounding private and mission critical type networks. Um, and so when you look at the three kind of ends of this triangle, the use cases we try to solve here, one you want to like enhance, you want improved mobility broadband. And you'll see like how that's achieved mostly is there's more spectrum that's used. And so you're going to get wider channels. You're going to get basically just more bandwidth available, um, which is needed, by the ever increasing amount of data that people are consuming. So that's more on the enhanced mobility. Then you have like the ultra reliable, low latency communication. A lot of like a lot of discussions at that time and still today is like around self-driving, like what are the applications that need very, very low latency? Like so 5G had to solve this. And then there's the massive machine types. This is your IoT, like your sensors, your devices. They also need to be connected. Um, and there's other features that we can get into as well. But one huge addition with 5G is millimeter wave. So that brought us that we call that FR2. And so millimeter wave has much, wider channel sizes. And, the range is much shorter, but especially for indoor application or even outdoor to a small degree, like there's millimeter waves where you're going to get those gigabit plus speeds very easily. One other big difference with 5G is the way that it's split out. So with 5G, the radio is now defined, it's split into different layers, where the radio is a DU and a CU. So with us, with Baicells, we can also do the split with other solutions, but for our Aurora, our Stellar, the CU-DU is still fully integrated. So you don't have a physical split with this, but just know with 5G, you definitely have the capabilities. So the part of the design and logic here is based on the use case, you might, push out the Geno B like layers and, further out or further in. And we have another slide that kind of shows this a bit better, but you have your front haul, your mid haul, your back haul. And so you could have like the Geno B at different, geographic even locations, than just putting it all at the tower, which would be the edge. But with 5G, a lot of things are getting more compute driven, a lot of off-the-shelf servers you'll see with Open RAN. So there's there it's more designed to be scalable for more of a cloud type solution, where before it was more of a black box and there wasn't a very well defined way or spec to make this work in a very flexible way. And here's just some examples showing those three use cases again. So if your use case is mobile broadband, you could have the DU right at the edge, and maybe like a little further out, you would have the CU, and then the UP user plane would be like at a separate data center, and then you have a more central, because with LTE, everything was sent to the central DC as far as the user plane goes. So you could be, there could be circumstances where you're in one state, but all your traffic's going to another state, in the carrier world. And so there would be a huge lag and latency here. So at 5G, we don't need to send everything to where the core control plane stuff's at. We can actually, move closer to the edge, the user plane. And then maybe even there we can scale up the CUs, so we don't have to put all the CUs right at the edge there too. So there's a little bit more flexibility that you have here. Uh, but if your application was ultra low latency, well, you might move that user plane all the way to the edge, because you need like as low latency as possible. And you might even put the server right there too. So that would be the low latency. And if you're doing IoT stuff with the machine type, you can just central place, pretty much everything if you wanted at a central data center, which is something, that's also a bit new to 5G. So when you're looking at 5G architectures, I tried to copy the LTE diagram, which is reference based, and put this into 5G to see what changed, what's different, how is it similar. So on the Geno B side, there are some similarities, but this would be like the reference-based diagram. So you have your Geno Bs connect to the AMF, so it's no longer an MME. The AMF is now where all the control plane signaling initiates from the Geno B to the core network. So you'll see the network functions within the core network, they're all renamed. So that's maybe the one thing you'll have to learn is if you want to dive into all the different, not that you need to. A lot of this might not even be that useful or important, but just to showcase what a simple diagram might look like, in a view that would be typical with LT world. So, but one big difference and change that actually did make it simpler with 5G is you'll see that the user plane, so instead of S1U, it's now called NGU. That goes to the user plane function. And you'll see most of these end with F now because everything's about network function. But the UPF, it doesn't have to be located, at the core data center. It can be located anywhere. So we even had a project where UPF is inside our base station with Blue Arcus support. So the UPF can be anywhere, and it doesn't need to funnel to another gateway to exit the network. So from user plane standpoint, actually the 5G makes this simpler, and improves latency this way. There are some functions. We'll actually go to the next slide. So this is actually what the 5G architecture really looks like in a proper diagram. So this is what we call the service-based diagram. This is really how the 5G network's designed. And so basically all the network functions can talk to each other. They don't need like a specific interface. They can all talk to each other via standard HTTP2. So this is a more cloud scalable design. And it's all about, scaling up network functions and resources as you need them. We'll actually go to the next diagram that shows kind of the hybrid of this. So now you can see the service-based architecture, but you'll see that they still draw like the reference-based point-to-point. Like you have your N13 between AUSF and UDM. But in practice and in reality, they're all communicating over the SPI message bus. So there's this common bus between all these network functions to allow them to talk to each other. So from base station side, again, they're just connecting to the AMF. So instead of so if you're configuring this on your radio, instead of connecting to the MME IP, you just need to know what's AMF IP. And then that's gonna from there, it's going to talk to the different network functions. Um, and yeah, so I think be easier to go to the next slide. Yeah, to do a quick overview. So some of the functions were split. So MME used to handle what now the AMF and the SMF are kind of responsible for. Um, and so basically MME got split into two functions. And then the HSS was split between the authentication function and this UDM. So some of the functions got split up, but then also some of the functions like that's gateway, P gateway are now just the UPF. So a lot of it's all similar as far as what do they perform. They're just either renamed and maybe they're more specialized functions versus doing a lot more before where they were with LT. Okay, on 5G channels, so this is the big change. If you recall, 20 megahertz was the maximum you could do with LT. Um, but now if we're in this FR1, the sub 6 gigahertz, we can go up to 100. There's some that were later added in later releases or updates. So we can actually do like a 90, we can do a 70. So there are more channels here. These are just what was initially defined. And you'll see that the number of bands have actually increased with 5G, but the band number that so if you're operating 5G in the same frequency that 4G was using, the band number is the same. So that makes it easy. So for CBRS, it was band 48. For LTE, well, it's also band 48 for 5G. So that makes that part easier. But due to the added bands and spectrums, you'll see that there's a much higher increase in numbers. And then you'll see the numbers way up here, this 257, 263. This is millimeter wave. This would be part of the FR2. So FR2 initially was supported up to 400 megahertz. The latest spec, release 17, supports up to 2000 megahertz. So this is where you get the huge bandwidth, to get the high speeds. And you can still CA. So all the talk we had about CA is still there. You can still aggregate multiple channels to get higher bandwidths. You can go between different bands. All of that is still the same as it was with LTE. So now to cover differences on the frames. So with LTE, we only had one subcarrier spacing, so we never had to define this or to configure it. The subcarrier spacing was always 15 kilohertz. So and although with LTE 7 symbols was one slot, where with 5G 14 symbols is one slot. So technically every 1 millisecond, if you remember with LTE, was a subframe, which was dedicated to downlink, uplink, or the special subframe. And then within that subframe, we didn't cover it, but LTE actually had 2 slots, but it just repeated those slots typically. But with 5G, we have lots of different subcarrier spacing options, and it's typical. Our radios are configured for 30 kilohertz. So 30 is going to be what you're commonly using in the mid-band area. So with the larger the spacing, the more slots we're getting. And the more slots you get, that is going to help to improve the latency for one. But typically these much bigger carrier spacings, you're typically going to use them in the millimeter wave. So typically 30 is like the commonly deployed option here, and that's what we use. So in our example, and what we'll talk about is this 30 kilohertz, where we got 2 slots per subframe. There's also something called, we won't dive into that much, there's something called mini slots. So that's one new feature within 5G. So instead of waiting For the next slot, like the base station could schedule another UE within that slot with like 7 symbols instead of 14. Um, so that can further improve latency and performance, but that's just an added function that 5G can support. So then if if you go back to the LTE, we talked about the TDD subframe assignment, and we had that chart that kind of showed what are the different configuration options between downlink and uplink. 5G doesn't really have a predefined table like LTE did. Like LTE had like 6 defined subframe assignments. With 5G, it's very flexible as far as you can set whatever pattern you want, basically. We as Baicells, we are kind of we did define some common ones that are popular in our radio to make it easier. But with 5G, there's not like a predefined table for the pattern itself. You also have control over the periodicity, like how many milliseconds the pattern goes for before it repeats. And the one difference with 5G is there's you have your normal symbols, your downlink symbol, your uplink symbol, but now there's a new symbol, well, F for flexible symbol. Um, Now in 5G, there's a there's a whole other feature. We don't support it, or we haven't had much use case or requirements or requests for it, but 5G does support dynamically scheduled like symbols. So when you, in your pattern, you can define which symbols are flexible, and then within that that subframe, those slots, you can define um, of those which are flexible, and then the base station could dynamically select uplink or downlink there. But there's I think at least in the carrier world, we haven't seen much request requirements for it, and I think part of it is it's when you do that, you're going to cause interference, likely, right? If you don't have everything timed up as far as your downlink uplink goes. But if you have some isolated cells, or maybe your indoor cells that are on different frequencies from your macros, there are some applications, but it is built into the spec that flexible symbols could be set so that they're not static. They could be dynamically set. So that's one uniqueness or difference here with 5G. So here is kind of a table put together showing the different patterns that we define in our radio that you can set. So here, to kind of walk through this, so if you look at the first pattern, we can see it's actually 2 different patterns of 2.5 milliseconds. Now, the assumption here is that it's a 30 kilohertz subcarrier spacing. So because if you remember, if you go back to 30 here, 30 you have each slot is 0.5 milliseconds, right? So if we go back to here, we can see that 5 symbols, or five slots, sorry, would be repeated. So there's 10 total. So if we assume that each is a half millisecond, then we have 2.5 millisecond plus 2.5. So we listed 2 separate because the pattern changed. It went down, 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 and then S. Now, in the spec of 5G, we've kind of seen it both ways, but technically this could be an F, but for legacy reasons, we still write S, like for the switching between downlink to uplink for the special subframe. But in 5G spec, they typically refer to this as the flexible slot. Okay, and then if we go to the flexible slot pattern, you can actually write this, we already defined 2 of them. But theoretically, you could put this to anything you want. But in our radios, we defined basically 2, so I repeated it twice. So when it hits the special subframe, which is, well, actually technically the flexible slot, then we can define within that how many are for downlink, how many are for, we say, F flexible, but in this case, the F would be the guard period, and then how many is for uplink. So with that, we can then count how many symbols are dedicated for downlink and uplink. So that's how we can get the downlink to uplink ratio based on what you set here. So you can see there's a lot of different options. In 5G, the highest performing though that you'll probably find are these small repeating patterns. So the ones that repeat every 2.5 milliseconds, like DDDSU or DSUU. So depending if you want more downlink or more uplink, these will perform the best because the time delay between the downlink and the uplink is quite short. And so this is where you'll find the best kind of performance and with 5G. That's where you take the most advantage. The issue is this pattern doesn't align with LTE. So if you're just deploying a private 5G network and you don't, if you own the spectrum or you're in a situation where you won't have heavy interference from, say, LTE networks, then deploying in these patterns probably will perform the best. But what I did is I marked if you were deploying next to a neighboring, say, LTE network, or you have an LTE network and you're just wanting to align with your own cells, then especially in CBRS, I still think these will be the better options here, as you'll ensure that you're still aligning to the legacy networks, which CBRS still heavily has a lot of deployments in. But if you're in an area that doesn't have 5G, or sorry, LTE deployed, then you might stick with some of these smaller patterns. But so what I marked here is the ones that can align, and the next slide I'll show you how do they align with that. So if we look at a 4G frame and we look at, this would be TDD2, right? Because we have 3 downlinks to 1 uplink, and then 3 downlinks to 1 uplink. So this top frame example is LTE. And then we look at a 5G. There's 2 5G patterns listed here. So one of them is 2 different patterns. So if we split it into this 5 milliseconds here, we can see, and actually let's go to the previous slide to make this easier to read out. So every 5 mil, so if we look at this TD2 at the very bottom, we can see that it goes for, the first pattern is 3 milliseconds, and so 3 milliseconds would be 6 slots. So DDD SUU. And then there's another 2 milliseconds, so that's 4 slots, DDD. So if that repeats every 5 milliseconds, that will align exactly with the LT frame. And in this image, you can see where F is what we would list as S in the previous slide. The other way you can do it, and so we can also do it with an offset. So if we just list the 5 milliseconds, so 10 slots. So we just list it out, starting with just the downlink. Because with 5G, you have to define the downlink, and then you define the uplink. And so you can only go downlink, switch, uplink in 5G pattern. And you can mix patterns and repeat them, but you have to do downlink and then uplink. You can't just go downlink, uplink, then back to downlink. The only way to do that is by doing 2 different patterns, like you see at the bottom here. So if we do the offset, you can see here there's a 1, 2, 3 millisecond offset right here. So if we did that, now we can define this. And I'll show you quickly, I guess, or getting towards the end here, where you can set this offset. But on your GPS sync page, you would set this offset to 3 milliseconds, and then you could align perfectly with 4G. So you have a couple options there. And then if you're doing that, you have to make sure that to match it with the special subframe 7, you can see at the bottom here, to match that, you must do 644 on your flexible pattern to perfectly align with that as well. Okay, so we're towards near the end here, and then I'll jump to the 5G base station. I think we're pretty close. On the 5G subscriber identifiers, so I just pointed out like what's a little bit different with 5G compared to LTE. So with LTE, we might always refer to IMSIs as the UE identifier. The SUPI is typically what we say in 5G world. And SUKI was a new feature added to 5G. So it makes sure that the SUPI, the identifier of the UE, is fully encrypted when it's transmitting during even the registration. Before you could decode this, now that's it's more secure in 5G this way. And then there's a global unique identifier. So the GUTI is that's another word for the global ECI in LTE world. And then instead of APN, you have DNN. So there's some things that were just renamed just because, but they have the same similar function. Then on the radio identifiers, instead of ERFCN, you have your NRAFCN, which is the frequency. We don't have time to go into the SSB, but this is different, or this is new with 5G. There's a GSCN. This tells the location of the SSB. And one thing that's different 5G is with LTE is LTE, when you connect to the cell, you're connecting to the center frequency. That's where the location of your RATCH or your random access, the reference elements are. So when you connect to an LTE cell, you know the full range of the channel. But in 5G, when you're connecting to a 5G cell, the NRAFCN that the UE picks up is the location of the SSB, not the center location of the 5G cell. So that usually trips people up a bit. There's a whole that's a whole other topic, SSB, so we won't have time today to dive into it. But with our base stations, we already kind of preset define what that is. And then instead of ECI, you have your NCI. So N standing for NR cell ID. And then PCIs. There's a bigger range, but the PSS is still 0, 1, and 2. So, and then on the QS, we didn't get too much into this. I'll just point out that there's QFI instead of QCI, and then the network slicing for the 5G core. So if you're working, say, at Blue Arcus, if you're configuring your 5G network, they will provide you with a SST, which is like the kind of your slicing number. Usually it's just number 1, but that's one thing that you might have to set on your radio. Yeah, and then you have your different tunnels that's more QS subject that we don't have time for today. And then this is the last page, just another quick brief of if you're just learning 5G, trying to understand the terminology, how does that equate in the LTE world? So yeah, I know we're pushing close to the end of the hour, so before we get there, let me try to dive quickly into what it will look like on the 5G radio. Now, what I will say is on 5G, it's on LTE, it's like the UX is quite mature. 5G, it's more like it's still fairly new. So this is more like an engineering interface. It's developed by engineers, so it's going to be not as simple as you might saw with the LT, but I'll show you where, basically where you need to go to configure the basic parameters to get things going. So yeah, we don't have the main dashboard, but I'll show you quick. You would go to quick settings. You'll need to use a calculator to determine what is the NRFCN for the frequency. So that's very simple. You can look up NRAFCN to frequency calculator. So you have to put in the NFCN number. We don't show you what the equivalent frequency is here yet, but you have your PCI. So again, you might want to make sure this is not the same, or mod 3 is not the same on neighboring cells with same frequency. You'll see that the subcarrier spacing you can't really change here. It's just set to 30. And then the bandwidth you can modify as needed based on spectrum availability and what you need. I have SAS turned off at the moment. That's why I can set this. Normally, if you have SAS on, you can't change these things. But you would change your downlink and your uplink to be the same. This value, this SSB, this is going to change automatically when you make changes to an FCN. So you don't have to worry about modifying this right now. So where you would typically go is, so once you configure your frequencies, so let's say you're not using SAS. SAS would be something else. SAS, I should go there quick. If you do CBRS, make sure you're updating the SAS page appropriately. But so let's say you got beyond that. On your advanced page, remember we were talking about the TDD slot config. So you go to your DU, and then from here, we can see the TDD slot configuration. So this is from that table I showed you earlier. This is exactly the same thing right here. So you would set your slots. So remember that last one is the one that is aligned with the LTE TDD2, or without any offset needed. And then you can set your special slot pattern. Make sure to this should be 644 if you're trying to align with TDD2. And you'll notice the last one's just 0. The reason is because if you look at the last 4 slots, because last 2 milliseconds is 4 slots, it's all DDDDD. So there's no flexible, there's no special slot. That's why it's all 0. So you'd make those changes. And then on the CU page, this is where you're going to add, actually on the AMF here. So let me delete this. I'm going to pretend this is new. So you would add your AMF IP. This is the IP of the core. So this could be the IP Blue Arcus, sets on their core. And then the local IP is just going to be the same IP of your base station, which in my case is this. And then you'd set your PLMN. This is the testing PLMN. But if this is, I don't know, we'll say this is 2. And then, okay. So that's how you do that. Now, if you have a different, one thing we didn't set yet is the PLMN. So if you go to PLMN page, you'll want to open your PLMN, and here you can edit. So I can edit this PLMN. I can add a PLMN. So just know that this is going to be the area. So before we even went and added that AMF IP and connection, we would want to go in here and edit the PLMN or add it, or yeah. So this is where you would change the PLMN numbers. And then remember the slicing, there's an SST number. You'll want to make sure that this SST number matches what's set in the 5G core. And that's really about it. So all the settings I showed you would be enough to turn this radio on, get it powered. We'll want to go to sync. You do want to make sure, if I'm lab testing this, I don't have GPS connected, so I'm in free running. So that's how I would run it. But in a commercial deployment, you would do GPS, GNSS. And then this offset, remember we were talking about the offset here? You'll want to make sure that, I think it's Oh, I might be off by one, but this is in NS. So if I was going to select a TDD pattern and I wanted to align it with LTE and I used the other method, this is where I would set the offset. Okay. So with that, once you had everything connected, you would see the cell active, assuming the MFIP was correct, the core is running. And yeah, that would cover the basic 5G configuration. So I think I summarized where you would need to be to configure things. If you're just doing this for the first time off the shelf, um, there are a few pages you need to go to on 5G. It might not be organized the best, but there's not a whole lot that you need to get configured to get it up and running. And I think the pages I highlighted pretty much show, the bare the requirements to get this up. So with that, I might stop sharing for now. I know I went a little bit over. Um, so, and I forgot to ask Paula, when you said 1 o'clock, I thought you meant my one, so I might need to clarify that there.
Can you repeat that, Jesse?
So I just realized 1 o'clock is, what time 1 o'clock are we going to do um the core?
We're in Pacific time. However, if you guys are ready, we can start sooner.
Yeah, I think maybe, I mean, I talked a lot for a couple hours now or more, so maybe for now, I mean, maybe we could do a quick open for Q&A, and then maybe take a break, uh, like maybe 30-minute break or so, I
Sure.
think, and then yeah, and then try to finish up. I could do more walkthroughs then if we have a little more time after that, and then switch to Blue Arcus from there.
Does anybody have any questions to type into the Q&A before we take a break? Okay, there's been none so far. Let's just take the break. If anybody has a question, please type it into the Q&A and we'll get back to those after the break. Do you want to take a 30-minute break or
Yeah,
what are you thinking?
I think we can, yeah, how about at the 30-minute mark, I'll come back on and then, yeah, we'll go a little bit further with settings now that I know I have a little bit more time. But I'll probably spend another 30 minutes overviewing things, and then we might speed up by a side check if the Blarkus team wants to present a little earlier.
Okay, let's come back on at 11:30.
Hello, everyone. Just getting back. I think we can start to resume. I did see there were some additional questions, so probably run through some of this firstly. So there's one comment about like in Europe, which bands the Nova range support. We have, like, as mentioned in the beginning, the products I was highlighting, like those are the ones you could buy today from channels, from our own inventory. Those are like the off-the-shelf solutions. Um, we have like we're a global company. We have many different products for other regions. So depending on the band you need, your requirements, we typically, we most likely already have base stations or CPs to match whatever the requirement is. So yeah, the portfolio is much wider. Today's was not trying to dive into everything that we do. It was, yeah, more for I guess our region and which is more focused on like private networks. But yeah, whatever bands you need, we typically will have that. Um, there's also a comment about bridge mode. So this This one's it also depends like by bridge, what what do you mean? But I'll try to show in the software we have we have a couple different options or ways to do this. So I'll do a quick show of where this is configured and then what exactly does it do. But for that, let me pull up some another document to show this as well. Okay, I'll go ahead and share screen here again. So on the topic of bridge mode, so this is, and I think where the trip up is and where this conversation usually goes is if you're in the Wi-Fi world, um, you can just, transparently bridge the AP and any device connects to the Wi-Fi AP is going to be on the same network, as you can, typically you can VLAN it out and so forth, but probably you can, just simply bridge it. In LTE, there's no, this doesn't really exist. You can't really bridge like the EPC very well. So there's a couple things like on the core itself. So I might actually start with the diagram here, 4G diagram to help explain this a bit. So in LTE, traditionally, normally you're going to send your user plane to the S gateway, then to the P gateway, and then the SGI interface is what exits the network. So on the core side, what you can do, and this is typically what we've seen done with like other vendor EPCs or cores, um, that if there's a bridge feature, you could bridge the SGI, but know that how this works is the when the UE attaches to the network, it is going to get an APN IP address. This IP address is sent by the MME. It's just one IP, right? So the packet gateway is, going to tell the MME like which, IP to assign this UE. So the UE is going to get one IP. Normally, this IP sits on the UE, right? And the UE in traditional sense is usually just like a mobile phone. Um, in CPE, it would be the same thing. Like CPE gets this IP, and then NAT's the traffic behind it. So if we bridge the SGI, what we can do is instead of the packet gateway instead of this being like a layer three, where but this is like a different network. Packet gateway has its own subnet and it's doing DHCP essentially. It's going to assign this IP to this device. Some cores you could make this SGI like a layer two. We had an option for this with our core as well. But you can do it at the core level. So that's my kind of point here. So you could then have basically when this reattaches, it's gonna so the challenge here is the same scenario. So as far as every APN is gonna get one IP. So this IP, it could come from the packet gateway, or maybe the core has a bridge function, which in this case, the SGI is a layer two, and it's going to do GCP discovery. It's going to get the response, and then it's going to take that GCP discovery response, and it's going to use that as the APN IP, right? And there's some trickery here because the challenge is we don't have a MAC address, right? This is the part of the trick. And this is like all the challenges that come with LTE. But without diving too deeply into that, you can do it this way. But and then you could bridge the UE, right? Let's say this is a CP, you bridge it, but you're only bridging one IP, right? This is the best and only thing you can do. Um, so this is the native way you could potentially bridge, but you're only going to be able to bridge one IP because every UE gets one IP. The other way, and we've done this with our core before as well, is establish like a layer 2.5. So like we have a GRE tunnel or a VXLAN tunnel. So you could tunnel. So from the CPE, you could establish a VXLAN or GRE tunnel to a server that runs on the core, and then that interfaces, out. Um, so there'd be a separate SGI just for the VXLAN or Jerry server. And then there now it behaves more like what a Wi-Fi IP would, where any device behind the CPE is now able to be on the same network, and you don't have to deal with just the single IP issue. So that was the issue with LTE, is there was no like real native way to do it in the same way that you could with Wi-Fi, just with the complexities. And this was designed for operator network, not for a home network or enterprise network. But there were later on LTE was introduced as a technology for such, but bridging wasn't like uh, it wasn't a thought out process when the spec was initially designed. Um, so this is so I would say from the core side is normally where you would do this bridging. And I think Blue Arcus would probably be I think they could probably comment further on their support level, what they can do. But if you're bringing it in the core, that's probably the best way to do it. Now we go back to the base station, like I'll try to comment about our Halo B. So Halo B is like this was our embedded core. We tried to make it as simple as possible. Um, and really it's just have your cloud key. So this is how the Halo B works is it runs like some of the core, it runs the core elements locally on the base station, but it's not like it's got the HSS, it's got that database of the subscribers sitting locally, but it's not like downloading everything, it's not going to hold the entire your like all your sims on this local database. So what happens is this cloud key that you enter, this is like going to be whatever is unique. So when you create a Cloud Core account, you're going to have this unique cloud key that belongs to you. So that's going to be the cloud key you enter here. And then, so that's how you provision that. And then what happens is then you manage your SIMs from Cloud Core. So this is how the Halo B works. So you'd have your subscriptions, you'd have your IMSIs that you go ahead and activate here. And then when the UE goes to attach to the space station, it will if that's right now you can see the SIM database is null. There's nothing here. So what happens is when the UE goes to attach to the cell, if it can't find the IMSI, it will then query the OMC, which then queries BOSS to look for that IMSI. If the IMSI is there, it'll go ahead and download that subscriber profile. So this is like so Halo B was like supposed to be like kind of seamless, and before we had Halo B we only had Cloudy PC, so we wanted it so that the same method you used, like we didn't want to change anything, so you would just enable Halo B and then you still use BOSS to manage your sims as always haven't been in the past. So that's how the sims would get downloaded. And the one thing though that's not running in Halo B mode is we don't really have like a packet gateway running. Um, and that's why we use LGW. So LGW skips the packet gateway. and sends the traffic out locally. So in Halo B, technically we could run the packet gateway, but it'd be like more CPU intensive. And we're running with very limited resources on the base station to get Halo B running really well in the first place. So we just run LGW. And you'll see there's different modes. By default, this is NAT. So how this works is, or how LGW works, is when the user attaches, it's going to get the APN IP. That APN IP is still going to come from the core. So even when you're in Halo B mode, there's still like an internal subnet that it's sending APN IPs, um, to your devices. And then when you have NAT mode, it's just going to NAT it so that what happens is every UE that attaches, it's going to get on the base station, there's going to be like a logical one-to-one mapping between the APN IP and the LGW IP. And if it's NAT, the LGW IP will always be the same IP as the B, and it will just be NATed to the B IP. So this works, if you don't care about, the NAT part of it. Uh, Bridge is what's commonly used. So we technically have this LGW bridge mode, but it's still technically doing a one-to-one NAT. So what will happen is when it's bridge mode, the B will do a DHCP discovery. So on this interface. And so you can add VLANs, right? There's a WAN LAN VLAN page. So if we want, we got different VLANs. But it'll do a DHCP discovery on this, and then whatever the IP comes back, it will then assign that to the UE. So the secondary channels I mentioned before is the MAC. There's no MAC address, so we have to like run like our own calculation to convert the IMSI to a MAC. So we actually have like a document that we explained how this LGW works, and the different modes, and explained like how does the MAC get generated, like in the case of bridge mode, which I think it's the bottom here. Yeah. So you'll do the DHCP. So it gets the MAC address is basically converted from the IMSI. But the thing is the LGW IP doesn't get sent to the CPE. The LGW IP sits on the ENOB, and then it does a one-to-one NAT to the CPE's APN IP. So it works like but the only issue is the IP is not sitting on the CPE. So, and if that's not desired, we have something called Halo B 2.0, but we still have it in kind of a beta. But if you want to test it, what we do that's different is when you use LGW bridge, it will actually pass the LGW IP as the APN IP. So it's like a kind of an update that we do there. And then you can do multiple, you also get multiple APNs, so you can do it a little bit more properly. So we do have this like Halo B 2.0. If you wanted to test the bridge, yeah, just you can let us know and we can enable it on your account. We actually have customers that have been commercially using it for quite a bit. So, but this is exclusive to our LTE product line. 5G, we are still like we don't really. I think we have a beta of it, but we don't. The Halo B for 5G is not commercialized, I should say. So if you buy 5G base station, you basically need to get a core. So that's the one difference. With LTE, like if you're just testing, getting started, deploying, you technically wouldn't need to get a core just for the basics of it. But the core is still very useful as it's going to have more feature sets than the embedded core will have. it'll do mobility much better. You'll be more scalable. So there's a lot of reasons you'd still want to probably get a core, with your network that you're deploying. But if it's really small and you don't, you don't not looking for the expense or complexity of adding something else, which I think is that further difficult. But in any case, we do have a way to do that, kind of coreless in a way with LTE. With 5G, at this moment, you still need to get a core. There's no cloud option. Halo B, there might be a beta version, but there's like that's at this point, we're still for commercial, we're still doing the local core, which could be through us, could be Blue Arcus. There's options there. So hope I answered some of the bridge question there.
Hey Jesse,
Yeah.
there's one more question in the chat.
Okay.
It's asking what is the bandwidth of the end user with 10 megahertz
Yeah.
5G
I saw
FWA?
that. I started to actually pull up a calculator for that before I got going on that. So, I mean, you can just Google. There's probably tons of spreadsheets. So there's like this website's decent enough if you're just trying to get theoretical. So I just put in like the configuration. Here's what I got for that answer. But there's a lot of assumptions there. That's like assuming, all resource blocks are scheduled to the user. That's assuming the highest modulation rate. But based on the question was for 10 megahertz bandwidth and 5G for 700 megahertz, right? So we know 700 is FDD. So basically you'd have 10 megahertz of fully dedicated, to downlink. So that part's nice. But if you looked at a 10 megahertz, so what I did here, we we could bump this. Yeah. So downlink actually this should be double. Sorry. So we have MIMO numbers. So how many layers of downlink? So we have two. And then I just left it at auto for determining what the MCS rate would be. And then I didn't touch the scaling. But knowing that it's a lower frequency, the assumption is we're doing 15 kilohertz for the subcarrier spacing, 10 megahertz, right? So that's the bandwidth there. But there's a lot of assumptions, right? We don't know what is the downlink to uplink. But you can play with these numbers and then you'll get, okay, so actually, if it's two layer, 83, it's not bad. So, all right, I see another question. For deployments of 5G, is there a template for copying GNLB configs? Well, I'm not sure the best way to answer that, but um, you can like backup save configs. Maybe you have like a golden config, maybe. There's like it really depends. Like if you're there's like features like within the OMC, for example, you could do like a plug and play. Um, if you had like common settings that you're looking to do. Whereas this maybe it's under maintenance. Backup restore. Here it was. Sorry, it's advanced plug and play. But yeah, at the moment it's just let's see GNOB. Yeah, the GNOB. Yeah, okay, never mind. There's there. So there is a function like we could do automatic upgrades. And we could, if we have like a set group of parameters we like to set automatically to each cell that we bring online, like we can do that looks like we could download like a template like from here to pre-fill in and then, input based on serial number what you want each one to be. There's if you're talking about a way is like to bulk like update things, we do have kind of a feature for that. But I mean the parameters I walked through today, I would say like I don't know that there's like this might be a template to start with, would be like maybe this one from this page and then maybe add parameters from there. Um, because the ones I walked through are like the basics that you would probably use for for setting each base station. Um, And if you're trying to like group them in a spreadsheet for managing them or tracking like the settings for each one like that, I guess you could do it that way. But yeah, there's not like a off the shelf, I don't think template that I could think of other than maybe what's in OMC here that you could reference. So not sure if that answers it directly or not, but yeah, so going back, go back to the LTE group here, base station. So while we still have time, I can walk through some other things maybe we didn't talk about yet. So if you're deploying LTE, the interfaces here are a bit, the UX is a bit more mature and nicer, but can point out some things here. Like right now, I don't have any UEs attached to this one, but if you did, you could click the UE detail. And this will actually list in a table all your UEs that are connected. One neat thing is it can print the IMSIs. And that's part of the LGW feature. If we went back to LGW, again, this is on by default. So if you're going to use another core, generally I always recommend just turn it off. Otherwise, you'll have issues with your user plane not working or not sending to the core, so you'll get confused. But if it's on that, you'll see that there's different ones. So if it's on, it will automatically try to grab the UE MZ. But if you turn LGW off, you have the option if you want to do the MZ catcher or not. If you're doing mobility, I'd recommend leaving it off because just the way that MZ catching works is if a UE attaches or during handover is sent and the UNOB doesn't know what is the IMSI, it will forcibly drop the UE and then have the UE reconnect until it sends the IMSI to it. So the user experience when this is on is maybe not good for mobility purpose. But if it's for fixed wireless, you can certainly put it on. It's not going to hurt much. But it is a little helpful because if you do have that IMSI catcher feature on, you can actually get the IMSI number. So if you're trying to troubleshoot the device, the UEs that are attached, you can actually see, which normally you can't from base station side. Normally you won't know what the IMSI is. You'd have to go to the core, look at the core logs to figure out, which one it could be. So yeah, but for troubleshooting, it's actually pretty nice if you're trying to figure out, well, if a user is having some issues, you can actually see exactly the metrics for it right here. And then you can always click the base station to go right back to the main page here. Okay, so what else? We have I showed the sync on the 5G side. On the B side, it's very similar. You have your free running, but you have other options. It's mainly your options are going to be free running. You normally only run free running for testing. I've heard some like for indoor scenarios, like people running free running and it seems to run okay, but per spec, you're supposed to sync, and to get the best performance, you should be syncing them. to avoid, interference issues or time drift and so forth. So if this is deployed outdoors, we would always run it in GNSS mode for GPS. If it's indoors or if the GPS signal is not good, we can change it to P2P, which is the 1588. And then we can configure that. But for this, you would need a local 1588 Grandmaster clock server for this to function. But one thing that, if you are deploying this for the first time, by default, it's set to GPS. So if you had a problem where you powered it on, you can, you thought it's configured correctly, but this cell will never go active. If it's always inactive, there's usually a couple things or a few things could be happening, but if you understand the setup flow of the cell, the first thing to look at is this synchronization. If it's not synchronized, it will never go to establish an S1. It will always remain inactive. So that's the first thing is now free running skips it. So you're in your free running, it's going to say synchronized. It's not actually synced. But if you're in free running, it bypasses it basically. But by default, it's set to GPS. So if you're not GPS synced, then that's a problem. So that would be maybe why you don't go active. The other is this, well, if it's CBRS, the other is this part, the SAS. Is SAS enabled and is it authorized? If SAS is enabled, but SAS did not authorize, your CBSD is not authorized to transmit, then the same thing, this will be inactive. And then, of course, if you're not connected to the core, you also will remain inactive. So if right now it's in Halo B, so 127001 is always going to be enabled or connected. But if you're connected to a different core with a different MME, then that will need to be connected as well. So those are the things to check for. If all that checks out, then the cell should go active. So some other things we can look at. Well, you can go to management server. This this is gonna by default already point to the OMC. You'll see the OMC URL here, and then the cloud key as well is here too. So if you have your own, if you're using the cloud OMC, you just want to make sure that the cloud key matches, what you put in there. That's how it's going to provision to your account. If you had a local OMC, or you have maybe even a third-party TR69 ACS server, you would put that URL here, and then save that. You can also, if you use SNMP, you can enable that here as well. If we go to, B settings, this is kind of where you have the name. So you'll see it's kind of got a generic default of the name of the base station, the serial number, but for commercial, you might want to change this name so that, especially like from OMC side, if you're monitoring, if you go to GNOB monitor, or yeah, GNOB, in this case, GNOB being LTE. So you can see the cell name here. But if you have a lot of cells, it's going to be easier to identify them by their cell name that way. All right, so I see a couple other questions coming in, or one more extra. Okay, so what's the requirements or prerequisites for an on-prem deployment of Cloud Core? So it depends when you use the word, yeah, so first we should identify which parts of Cloud Core. So when we talk about Cloud Core, actually there's three pieces of Cloud Core. You can see there's three tabs. And one of them like she actually can't even control. But there's the EPC or core, 5G core, like depending on what is it 4G or 5G. Now, The EPC side of it's not really used anymore, it's very rarely, because ever since we introduced Halo B, like there's almost no like cloud MME connections. So there's that part. There's the OMC part. The OMC is where you manage your equipment. This is our NMS type solution. And then there's BOSS for billing, that's more for managing your SIMs. So there's different pieces of Cloud Core. So when you say like for local, if you want to deploy this yourself, typically what's deployed locally is you're going to have the OMC. So the OMC can be deployed local, and you could just deploy the OMC if you want. And this would be you would do this if you have like your own core. So if you got a core from Blue Arcus, you would from us if you said, well, I have my own core, and I don't want to keep paying for Cloud Core, use Cloud Core. I don't want to be on the cloud, right? If that's your desire, then you could just buy the local OMC from us, and you only need the OMC because you already have the core. You don't need BOSS because BOSS interfaces with our core. So when you go with a third-party core, you would use their core, their BOSS systems. So from us, if you wanted it local, you don't want the cloud, then you would just go with the OMC. Um, Now the OMC, you would just typically it's just deployed as a VM. So what we do is we provide you like the requirements, like how much CPU, how much memory, disk space do you need, and then you would deploy um, OMC yourself. You can certainly get a copy, and typically we can even offer trial keys, but there is a cost, right, for a permanent license of it. Um, the other option you have is if you wanted, say, full end-to-end Baicells, you would get the OMC, the BOSS, and the core from us. And it's the same as like if you go local MC, like so instead of one server, so if you just want local MC, and then go with your own core, um, that's just one VM, right? That you would need. If you go with the full end-to-end buy cells and you want to keep that local, then well now you have buy core, you have OMC, you have BOSS. So that's three servers you'd be spinning up. So, but in all cases, we would just provide you what are the system requirements to run the software. Okay. Um, let's see. So going back to the multi radios, just seeing if there's anything else to point out while we're here. We covered SAS sync management. Um, for mobility, I mean, this would take a bit to walk through everything, but if you are doing a mobile network, um, for mobile networks to work for handover, you would be adding like your neighbor cells. So this is where you would add, any your neighbor frequencies, your neighbor cells, and that's gonna be how the measurements take place and the decision making of whether or not to hand off to your neighboring cells. If we go to the mobile parameters, there is a couple things additional. Like these are all things you would tweak if you're doing mobile. Um, there's a lot of maybe noise here if you haven't done this before, but um, essentially you're setting the different threshold levels of when to hand off, when not to hand off. You're just setting, these are all the flexibility of how you adjust handoffs, and a lot of times it's doing a lot of walk testing to determine and then tweak the settings appropriately. But some things that are not exactly handover related that are worth pointing out. One is the cell selection here. So this might not seem like much, but it determines like at what signal levels are you allowed to attach. So you just take this value and you double it. So this would be a minus 130. So that means at up to minus 130 dBm, and I think it's minus the offset, so one, so maybe 129 dBm. So at that signal level, the UE can attach. Now that's pretty cell edge, that's pretty poor signal. So if you didn't want UEs to attach at those weak levels, you could always modify this. Like maybe you say my cutoff is minus 120. So for user experience reasons or trying to set the cell edges, this is like one parameter you could do to set that. So that's a kind of important point I'd like to point out. And then you could also go the reverse. You could say, I don't care what the signal level is, let it connect. So if you do minus 70, that's minus 140 that a UV could connect up to. But of course, it wouldn't perform very well, but you'd at least give it some connection. So this just increase or decreases the cell edge, just by simply informing, because this is what's broadcasted in the broadcast message. You're telling the UE before it even tries to attach, like, is your signal level allowed or not? And lastly, in the advanced section, there's a couple things to point out. You have your UE and activity timer. Right now it's set super high. This is by default, the product's kind of tuned towards fixed wireless. So what this means is like it will wait 60,000 seconds before, and then it has to do that 20,000 times before the UE goes idle. The only reason it's set super high at this is because a product was heavily used for fixed wireless. That's been shifting a bit now. But if you are doing a proper mobile network where you want UEs to idle, and you usually want them to idle for power consumption reasons, or you just have a lot of users, and you don't want them all camped on your cell taking up, the active count. So in this case, you could reduce it. You could say, I want, after a minute and maybe even a couple counts, or maybe 30 seconds, you could modify this so to push the UEs to go idle. But just know by default it's pretty high. And you can always double check to make sure that the modulations are enabled. So sometimes this might be disabled. They should be enabled by default, but if you wanted higher modulations, you can control that here. There's some more advanced little settings here, but those are the things I'd point out. The last things I might point out is we have a spectrum analyzer tool on the LT side, which is kind of nice. So if you're troubleshooting, like your users are dropping, your performance isn't good, and you suspect there might be some external interference, firstly, I would say from the CPE side, I would run a scan, um, which, uh, yeah, so on CPEs, there is like a cell scan feature, or cell survey, and that will print out all of the cells it can see. So that's a probably quicker, easier way to do that. But from the B side, you also have options. Um, Normally, what I would recommend is if you do no load, this will kick the users, but it will give you an accurate depiction of what's going on. So actually, I can do this really quick. So what this will do is it will measure the, this is a 20 megahertz, so there's 100 resource blocks. So this will give us a quick reading of, is it picking up any noise? Now, it's a little normal for noise to be at the very center channel. So if you see a spike here, that doesn't necessarily indicate anything bad. It's just picking up its own noise. But if you see any bursts outside the center, that would, be an indication. In this example, I don't really see any noise, but you could also do a full band scan, which will try to scan the entire band. And it does it in 20 megahertz increments, but that would give you like a full reading of the spectrum. But this is a quick way to get a quick reading. And then when you're done, always make sure to set it back off so your users can attach and be fine again. And then there's some diagnostic stuff here. If you're trying to do signal traces, you can do all that here. You could point it to your PC running Wireshark to do the RC or SCP signaling traces. You could also back them up locally. Down here, you could say, I want to back them up both. I just want to run a PCAP for 15 minutes, start it, stop it, download it. So you can do that as well. So if you're more advanced and you want to, get PCAPs of the signaling, you can do that here. And then then there's just the basic diagnostics. So you can ping trace route, you can iPerf, make sure you got the backhaul bandwidth or so forth is good. So from LTE side, yeah, I think that covers a lot of the basics there. 5G, there's a lot more things to tune and adjust, but what we covered previously are like the main core set of fields that you need to change or modify potentially. Um, and then over time, our 5G product line should have a more similar user experience as we are with 4G, but at the moment it's more like an engineering interface. Let's see, double check if there are any more questions. Um, Paul, you think we're ready to switch over, or we have a little bit more?
We can go ahead and take a lunch break. They're going to be coming on at 1 p.m.
Oh, so 45 minutes from now?
Yeah.
Okay, that's quite a bit. Okay, I wasn't sure if they're gonna come on earlier. Um, yeah, I sped this up a bit, didn't got the times mixed up, but yeah, normally these run a little longer. In person with a lot of more questions, but yeah. Um, I think the goal for today was really to just cover what is necessary to spin up a network, whether that's 4G or 5G. The things that we didn't really cover on that regard is on the core side. Again, on 4G, you could just use Halo B and Cloud Core, and you wouldn't have to worry too much the core. You can certainly get third-party cores like with Blue Arcus and get a lot more functionality there too. But it's easier to spin up a 4G network. 5G, you're certainly going to need another core. And that's where, I think we'll let Blue Arcus talk through what does that look like. Like what's the core, provisioning setup process look? Because the radio side, there's some parameters to tune as we went through, right? We want to know but mostly we're just pointing the radio to the core, and the core does the rest. So we just need to know what is the core's IP. And other than that, we're just setting the RF settings, right? We're setting what my channel bandwidth is, what's my TDD slot pattern. Um, those kind of basics you're kind of configuring on the radio side, but a lot of like once you connect to the core kind of, does all the signaling from there. So SAS is another piece that didn't I guess do a full demo on, but I'm not sure too here how much of the audience has CPI'd or experienced or even cares for CBRS. I think we have a mix of different regions here. So yeah, I think this is a good spot to pause for now. Maybe have another break and then yeah, by 1 Pacific, I think Blue Arcus will come in and demo their core and walk through that. So uh, I guess before we pause, if anyone has any further questions, please let me know. Run through that. Otherwise, we can maybe do one more Q&A right afterwards. And then, of course, we're always available for any follow-ups that come up by then.
We plan on starting back up again in at 1 p.m. Pacific time. So we'll just take a quick lunch break, and then at 1 p.m. Pacific time, Blue Arcus will be doing the core demonstration.
To 5G, how did customer signals change? Yeah, so on that question about switching, say, from a 436Q to, say, a Aurora 243, in this case, the mo for the most part, the problem is the restriction of the ERP of CBRS. So you're not really getting power gains, right? So switching from LTE to 5G doesn't mean you have higher power. So the signals won't necessarily be much different. So what you're really gaining with the CBRS, or sorry, with 5G is you're gonna get a little bit. I think the like if it was like bits per hertz comparison, you'll get a little bit of improvement because there's a little bit more efficiencies. The guard periods aren't as wide compared with 4G, so you're getting more resource blocks and elements. So you're getting a little bit there. The downlink, I think, bits per hertz wise, is not going to have a huge improvement, but the uplink, I think you'll see at least doubles if you can get 2 streams of uplink. And you get higher modulation on the uplink as well. So I think where you see benefits is especially in that direction. But to take full advantage of 5G, if you're just talking about like bandwidth, you need the higher, larger channel sizes. Um, and I think the challenge with CBRS is just the nature of the band and how it's shared. So in 5G, it would be nice if and if you're rural or maybe even indoors, like you could probably find, 80, 90, 100 megahertz. Like that might not be too difficult in one channel. But in urban areas, you're probably not going to find 100 contiguous megahertz. So you're not going to get the full usage, I think, that 5G can offer. Um, so I think that's the challenge. And then with our first gen 5G radios, they're single carrier only. So the problem is if the shared band, such as CBRS, has a lot of non-contiguous chunks to it, then you might not be able to get any higher channel sizes than you could with LTE. So that's where the next gen. So we have like a second gen Aurora coming some point next year that would have 2 carriers. We already are doing trials of it for other bands like band 41. But for CBRS, the moment we just have the single carrier version of it. So what I seem to tend to notice still is the LTE is still more commonly deployed than 5G. 5G, of course, has the greater interest, but the cost and simplicity of 4G, without having to have the core initially is we still see the 4G is And it depends on the application too. Like if you don't have huge bandwidth requirements and you're not trying to get, push the most amount of throughput as possible, then, LT is a little bit more mature there. So, and the price points I think are better. So, but if you're already, if you're determined on 5G for, you know, the other extra benefits it has, and you're gonna have a core, you have the budget for it, then yeah, we definitely can support that. But I would say signal levels, if you're just on signal levels, I don't think there is gonna be a big change there, just going from 4G to 5G.